Welcome to the seminars of the Statistical Physics and Complex Systems groups of the University of Granada. Today we have a talk from Beatriz Olmos. Beatriz is a professor at the University of Tübingen. She made her PhD here at the University of Granada under the supervision of Jesús Sánchez de Esa and Rosario González. Then she moved to the University of Nottingham. I think I'm not missing any thought in the middle. She were there in Nottingham for several years. How many years?
10 years.
10 years. Well, many years, and then she moved to the University of Tübingen. She works mostly in things about atomic physics and quantum optics. And today she's going to talk about the collective couplings on array of atoms. So thank you very much. Welcome.
Thank you very much. Okay, thank you for the introduction. So yeah, first of all, obviously, thank you very much to Danny and obviously to everybody in the Institute for inviting me to give this talk. It's been a while since I gave a talk in Granada, and well, even more in person, but hey. We'll take it. So yeah, as Danny was saying, I'm currently based at the university. Sorry, I shouldn't do this. I wanted to have a laser pointer. Okay, so as you can see, I'm here at the University of Tübingen. This is in the south of Germany. I'm here since end of 2019. But I also keep a partial part-time contract at the University of Nottingham, where I'm still a lecturer, and I have some things in common there, but yeah, mostly I am basically based here now in the University of Tübingen. So yeah, most of my talk today is going to be talking about atoms near nanofiber. My working hosts, generally the things that I work mostly on are quantum optics, and in particular, I'm interested in what happens when interacting systems coupled to the light, and this is going to be basically the common theme of this talk today. So, but before I get started, okay, first of all, if you have any questions at any time, please just ask on the fly, because if I lose you at the beginning, then I don't expect you to understand anything towards the end. So please just ask, okay? Good, so let's get started. What am I talking about today, okay? Today, this is kind of a summary of the system that I'm talking about, and don't worry, I will explain each one of these things a bit more carefully, but I wanted to give you first an overview of the topic and then go a bit more into details. So this is the system that I will be talking about. I have a nanofiber or some waveguide of some kind, okay? And I have some atoms, these little dots here, you can see, these are representing atoms that have some, and these, arrows there have some transition dipole moment. Whenever I talk about atoms, or in general emitters, I will be talking about something that has two internal levels, so some ground state and some excited state. And the distance, the energy distance, so to say, between these two states is going to be parameterized by this wavelength lambda. Okay, so things to keep in mind for later. I will repeat this, but still, lambda is this energy distance. And then the only extra bit of information is that I have, I'm coupling these atoms to a nanofiber or to some waveguide of some kind. And I will explain you what this means in particular, but generally speaking, the difference between having atoms just by themselves and having them next to a waveguide or next to a nanofiber in this particular case is that whenever an atom emits a photon, so let's say you have an atom and you have the atom in the excited state, this will eventually go down to the ground state, and we all know that, right? But now this photon can be emitted now not only into the radiation field in general, which I will be calling unguided modes, okay, because these are unguided, right? But they can also be emitted into these guided modes, okay? The good thing about these waveguides, about these nanofibers, is that you can emit a photon into them, and once the photon is kind of trapped into this waveguide, it can be losslessly taken from one side to the other. And then the good thing is also you can put a detector at the very end, and then this detector will detect all of these photons that come. And yeah, you can analyze the light, you can think about many different cool things to do, and I will show you some of them. Now, the only extra thing that I haven't told you about is, of course, okay, if I'm putting the atoms into the excited state, is because I'm driving the system in some way, because otherwise my atoms would be always in the ground state. And this is the function of this laser that I have here. And just, again, I will repeat this, but yeah, it's coming with some momentum K. And this momentum forms an angle theta with respect to the chain of atoms that I will be considering. Okay, so this is very generically what I want to talk about. Why is this interesting? As I say, because you have a finite number of these guided modes. So you have usually a couple of modes that are guided, and then they travel longitudinally. Once the light comes from the atoms and goes into this waveguide, it's losslessly transported along this waveline, along this fiber. And B, because also very interestingly, what you can do is you can put your atom, and depending on the orientation of, let's say, the polarization of your laser and the dipole moments, you can actually make the emission chiral. What does this chiral means? This is kind of abuse of language, because usually chiral means that you have the same probability from one side and to the other. So to say that that's chiral symmetry. So basically what you can do is you can break that chiral symmetry. In easy words, what this means is that once the photon is emitted into the guided modes, you can make this photon be more likely emitted to one side than to the other. Okay, so imagine, and that's why I put here, for example, in this case, this line a bit thicker than this other one. Okay, so this is what I will be calling later directionality. Is simply that once the photons are emitted into the nanofiber, depending on the polarization of the laser, depending on how far the atoms are from the fiber, etc., you can actually make this emission directional. It prefers one direction instead of the other. And this, you can think of it as something also cool, because, okay, you can actually have a system in which you have all of your atoms, and then, the photons are emitted into the waveguide, but not in both directions, but actually only into one. And then if you have a detector on the other side, you can, grab all of the photons that are then emitted into the nanofiber. So, as I say, this is kind of a summary. If you didn't understand everything, it's okay, because I will be coming back to the details of this in a second. But just to give you also an idea of why this is interesting, okay, this is actually not only theory, but I mean, people do this actually in experiments, which I find absolutely ridiculous. I mean, how, right? And look, I mean, for example, this is an experiment. I mean, this is kind of the system that I will be talking about today. Is basically a nanofiber with these atoms nearby, okay? But not only you can put a nanofiber, you can also, as I say, this is kind of general. You can generalize all of these concepts to other systems that are not a nanofiber. Nanofiber is just, very thin silica fiber, okay? But you can actually do this also with other things. Here, I just show you some experiments that work with this waveguide. Okay, this is a waveguide. You can see here, you trap the atoms in there, and then you couple them to these guided modes of this waveguide, and then you have the same effects, basically, even better in principle. And here you can also do similar things with so-called 2D photonic crystals. And this is just another system in which you can couple emitters into guided modes. Okay, so this is kind of the working horse. So all of this is very good and well, but okay, let's now take a step back. Okay, so obviously all of these things are interesting from the quantum information point of view, because as you can see, I mean, it's nice because you can have atoms that emit a light, and then you can transport the light, and that light can have information. You can have some quantum state of light or whatsoever. And the good thing is that you can transport it from one side to another, and then you can maybe emit it again, or it be absorbed by another bunch of atoms, apart from some other fundamental interest. So But before I go into many atoms coupled to the waveguide, let's talk about what happens with one atom, okay? So I have, let's say, one atom. I have one atom that it's at some distance, h, from the surface of a nanofiber. Now I say this is a nanofiber, and then as I promised before, this is just a two-level system, ground state, excited state. And you drive it with the Rabi frequency of the laser that is given by this omega. So this is how strong, it is related to how strong the driving is, okay? So how much intensity your laser has. And also you have some detuning of the laser. So how actually far off resonance you are. On top, that's kind of what the laser does, but the atom itself is coupled to the environment. And as a consequence, as I say, if it's in the excited state, it will eventually emit a photon into the ground state. Now, it can emit into the unguided modes, and that will be done with a rate that is this gamma U, okay, gamma unguided. We will not see a lot of that, but I wanted to write it for a second there. Or it can be emitted into the guided modes. And if it's emitted to the right, here I have this rate, gamma right, and then I have this gamma left, okay? So, and these two don't necessarily have to be the same, as I said before, because of this chiral coupling of the atoms to the nanofiber. The total emission rate then, so the probability, the rate at which the atom in general emits a photon, it's given by this big gamma, which is just the sum of the three. Good. Now, what's the challenge here, basically? Okay, if you want to, in principle, okay, imagine you have the system and then, okay, eventually what you want is that you want, ideally, that if you drive this atom, all of the light or most of the light is going into the nanofiber. Why is that? Because if it's going out of the nanofiber, if it's going into the unguided modes, basically those photons are lost in a way because you cannot really catch them. While if they go into the guided modes and then you, just a second, and then you put here a detector, you are sure, so to say, I mean, of course there is a detection efficiency and everything, but at least, you know that the photon is coming here and then you can detect it here and then you can analyze the light and you can do whatever you want, okay? You can make a click, for example, every time a photon is emitted and then you have, the emission rate, or you can actually analyze the light by doing, I don't know, homodyne detection or anything, but at least, I mean, you have it kind of under control. So what you want is really, to maximize the what beta factor is, as you can see, is basically just the probability of the, if I have a photon that it's emitted, what's the probability of it being emitted into the guided modes versus the total emission rate, okay? So if this is 100%, it means that all of my photons are emitted into the guided modes, but actually what happens, and this is what I want to kind of show you here, this is just for, no matter what you do with your, with the distance between the atoms and the nanofiber, or with the wavelength of the corresponding transition, the ground to excited transition, no matter what you do, you really cannot go much farther than usually a 15 to 25% beta factor. Actually, usually in actual experiments, this beta factor is even lower than that. So in practice, what happens is that if you have one atom, a lot of the photons are lost, so to say, into the unguided modes. Now, another challenge, as I said before, would be, ideally, if you want to, you want to be able to also control the directionality. So how many photons are emitted if you have, for some reason, maximized this beta factor, you want to know, so to say, if your photons are going to one direction and to another. Whenever I talk about this, I want to talk about how directional, so to say, this is, and this emission is. I'm going to be talking about this directionality. And this directionality D is just, this gamma right minus gamma L divided by the total emission rate into the guided mode. Okay, so if this is equal to 1, it means that all of my photons are going to the right. Minus 1 means that all my photons are going to the left. And 0 means that I have equal probability of going one direction and the other. So now, ideally, as I say, I want to be able to control this. The problem is also that just controlling, so to say, how close the atom is, and for usual experimental situations, you can also only control it up to a point. You cannot really make it completely directional. So
sorry, one question.
Yes.
Here you only have two parameters to calculate the d and the beta, that is the wavelength of the light and the distance between the atom and the...
What I am changing there is, yes, it is. I mean, this RF, I didn't talk about, this is the radius of the fiber, but this usually fixed.
Okay.
Yeah.
Okay. So you are only changing the h and the lambda. Are there any other factors that to take into account?
You could, for example, I mean, for example, for the directionality in particular, but also for the beta factor, you can also change the orientation of the dipole moment. And actually that is what eventually, so you can, for example, excite something that is circularly polarized like here, and you can take that and maybe you can turn it around in this axis, or you can turn it around in this other axis. And this we also checked, for example, for this single atom. But the thing is that to actually get a full chirality to one side, so to say, to have directionality 1, for example, you would have to have a very specific elliptic polarization that it's not really practical, so to say.
Okay.
Exactly.
And the tuning for it? No, but this depends on lambda.
Exactly. So this is kind of extra. So at the moment, I'm not driving, so to say. So the properties that I'm showing you here do not depend on the driving of the atom. This is intrinsic properties of the atom. It's literally you put one atom in the excited state and you look at emission.
And what happens?
Exactly.
Okay, I see.
Good. So then, okay, these are kind of the two challenges that we had in mind. And before, we started this project, and then, these challenges, I will show you in the next few slides, can be addressed by exploiting the collective interactions between the atoms. So more atoms is better than having one atom, okay? So this will be what you will learn, hopefully by the end of this. So, but before that, I have to, kind of take a detour, because, if I have many atoms, things are better, but to explain you that, I have to explain you why, how to describe to a nanofiber. And the good thing about this is that I don't really need to explain you exactly how many atoms couple to a nanofiber, because one equation actually rules them all. Okay, one equation, the master equation, can already show you how many atoms couple to an environment, okay? I don't really have to say if this has a nanofiber in it or not. I will get into this later. This will be enough to show you the structure, so to say, of my equations. So what is the problem that I have here? The problem that I have here is just, as you can see here, there's many atoms, right? And then I have some environment. This is kind of given by this blue blob on the background. So what I want to do is I want to just obtain an equation of motion, not for the atoms and the environment, but I actually only want to know what happens to the atoms. I want to obtain a master equation that describes me in this row, okay? This is the reduced density matrix that describes only the internal degrees of freedom of the atoms. I'm sure that, most of you have seen this before, but still, I think it's worth saying it. So now, what you obtain out of this, what you are doing basically in practice is tracing out the radiation field. You're tracing out all of this environment, and as a consequence, what you get is an equation that tells you that there are some interactions, effective interactions, that are mediated by this environment between the atoms. And also, it will give you some sort of weird dissipation, so to say. So this is the equation, that you obtain, and I will break it down in a second. But before that, I just have to point out also that this kind of master equation, I say that it's valid for all environments. That's not exactly true. You always have to be careful anyway that you are within the dipole approximation, that you are within the Born-Markov approximation, so your environment has to be Markovian, okay? And also, you have to be within the rotating wave approximation for this equation to pop out on the other end. Okay, so, but if you believe me, okay, that all of these things are valid, what you obtain is this master equation. As I say, rho is the reduced density matrix that contains the degrees of freedom of the atoms only. And now what I have is two parts here. I have a Hamiltonian part, as you can see. This is kind of, if I didn't have anything else, I would have just a von Neumann equation. So this could be basically, yeah, just a Schrodinger equation, okay? And then I get out also something that is this D of rho, which is the dissipator. So this kind of tells me what kind of coherent processes happen. And this tells me what kind of dissipation processes happen, coherent versus incoherent, if you want. Now, just one important thing. This is the thing, everything that comes out of here is just because I have atoms and they are coupled to the radiation field. This is something that anyway one cannot avoid. So this is kind of the cool thing about this, is that just the atoms doing something that they cannot avoid, which is interacting with the electromagnetic field, gives rise to cool effects. These cool effects are, this Hamiltonian actually looks like that. This is a Hamiltonian that looks like some coefficient here, and I'm not going to enter into how this coefficient here looks like. And then I have this sigma j dagger sigma L. Now these sigma are just the ladder operators. So basically what this Hamiltonian is showing me is flip-flop interactions between two atoms. So if I have an atom L, so to say, excited, then this kind of process what it will do is it will bring it down to the ground state, exchange a virtual photon, so to say, and then make another atom, the jth atom, go up to the excited state. And that will happen at a rate that is given by this V. Okay, these are these dipole interactions, exchange interactions. And again, these happen for free, so to say, and they can actually be very strong. And yeah, they will obviously depend on the system that you have, but in general, yeah, you can have very, very strong interactions between the atoms. And then you have the second part, this dissipator, and this dissipator is just, yeah, this over here. And I call this box collective decay. Why do I say collective decay? Look, I mean, in general, I mean, maybe some of you have seen already, yeah, this kind of equation, the Lindblad equation, and you know how to identify, if you have an equation like this, you know how to identify emission processes and jump operators, so to say. Emission processes or jump operators, if you want, and the corresponding rate at which this happened. Now, this is not quite there, because as you can see here, you have an L here and a J here. So these are not really, so sigma J itself is not my jump operator. So I don't have simply an atom that decays from the excited to the ground state, and that happens with a given rate. So, overall, what happens is that this matrix here is in general not diagonal. Now, if I want to know what are the processes of emission and the corresponding rates at which these happen, what I do is I diagonalize this matrix and I can obtain these decay channels and rates. So I don't want to go too much into details because I have to explain you a little bit about superradiance and subradiance, but this is the point. Now I diagonalize this, let's say I have two atoms only, okay? If I have two atoms, what I have is a 2x2 matrix, right? So let's say I have my matrix here, and that could be, in the diagonals, what I would have is just my single atom decay rates, as I should. And then I have also some off-diagonal elements, and I'm going to call this now gamma 1,2s. Now, what happens? The good thing about this is that I can actually diagonalize this very easily, and I obtain two types of, two possible decay rates. I obtain a decay rate 1, which is just gamma plus gamma 1,2. And I have another one, which is gamma minus gamma 1,2. Now, what happens? If this, I have kind of two options, or two extreme options. What happens when gamma 1,2 is equal to 0? When gamma 1,2 is equal to 0, then I have that this matrix was already diagonal, basically. So what I will have is that my natural emission modes are indeed the ones of, so let's say here, okay, so I have, if gamma 1, 2 is kind of 0, then I have one emission mode that goes with gamma and another emission go, sorry, not that gamma, the other gamma, one emission mode that goes as gamma and another one with gamma. So this is basically atom 1 decaying with emission rate gamma, or atom 2 decaying with emission rate gamma. That's kind of the boring situation that I will promise you won't have now. But now what can happen if gamma 1, 2 is actually on the order of single atom decay rate? Then what happens is that I have two processes, one that goes as 2 gamma and another one that decays with gamma decay rate 0. What do I have here? I have one process that of emission that decays much faster than the single atom decay rate, in this particular case twice. So this has a super radiant state, okay? That's what's called a super radiant state because it decays very quickly. And then I have another one that is a subradiant state. Why subradiant? Because the decay rate is smaller than the single atom decay rate, and in this particular case it's even a dark state completely, because if I have a state that it's eigenstate of the dissipation and that has that decay rate, that means that that state, so if I have an excitation in my system that conspires such that it's an eigenstate of this matrix, then that state won't decay at all. That excitation will be trapped in my system forever, okay? So even though I'm coupled to the environment, I can ideate situations in which the excitation it's not to them. So all I wanted to say is that the decay is collective. You cannot really see it as one atom emitting one photon and that's it. You have to see it kind of as a collective process. And now, obviously, what I haven't told you is exactly the shape of these matrices VJL and gamma JL. And this is because they strongly depend on many things, okay? As I said, there is one equation to rule them all. So it depends really on atomic dipole moments, so the specific polarization of your atoms. It depends also on the radiation field structure, so whether the atoms are in free space, whether they are, for example, coupled to a waveguide, as I will have them, whether the atoms are in free space, but then I have a surface nearby. All of those things will change the shape of those the matrices, okay? And as a consequence, it will change the way that the atoms interact with each other and the way that the atoms are emitting photons back into the environment. And finally, it will also depend on the specific geometry. It's not the same to have a disordered gas, for example, an array of things. Okay, so this is kind of to explain you where some of the things that I'm going to be talking about later come from. Okay, so this is kind of end of the detour. Let's go back to my system. I'm going to talk about collective light matter coupling on a waveguide. Now we know what happens with one atom, and we know kind of what could happen with many. So again, what I have is now a nanofiber. I have many atoms that are coupled to this nanofiber, and then I have a laser that is driving them, because otherwise I wouldn't have photons to emit, so to say. And then I'm going to be, from now on, collecting the photons, only the photons that go into the right part of the, I place a detector, and that's what I'm going to be taking, okay? The equation of motion for the atoms, I can do exactly the same tricks. I Bohr Markov approximation, tracing out the environment, etc. And then I get this master equation. As you can see, this is exactly the same one that I had before. It's just that I have added one term here. And this term is this H laser, okay? So this I'm not going to write down explicitly, but this is just taking care of how the laser is exciting the atoms. It's a very common thing. This contains, again, that there is a radio frequency and there is the tuning of the laser. Okay, so that's just describing that part. And then the rest I showed you before. This is just these dipole-dipole interactions. And then finally what I have is this dissipation that is collective. Now, But now I have a specific system. I have a system where I have guided and unguided modes. How do I take that into account? And I'm going to be focusing particularly on these gammas, okay? What I can do, that's the good thing, is that the mathematical construction allows me actually to separate the tricks and separate them, because actually the character, the character of these matrix elements is very different. Okay, I have unguided and the guided ones are very, very different. In particular, the ones that are guided, okay, so both the coherent and incoherent couplings, actually also these VJLs, give rise to couplings. So if I write them down, they are all-to-all. What does this mean? That, for example, the strength of these interactions, of these flip-flop interactions, does not decay with the distance between the atoms. This is if they are guided, okay? So basically you can think about this as, okay, if this atom here decays, now I have here something that is guided and is lossless, okay? So I have basically just a plane wave that is transported across the nanofiber, and then it goes up here, and this one then goes to the state. Again, this is a hand-wavy way of seeing it. I know that here the process is not like that, but okay, you get an idea. So the guided modes give rise to all interactions, coherent and incoherent. So you have something that looks like an exponential of ij minus L, so to say. Okay, so it really doesn't depend on the distance, only up to a phase. And the phase will become important later, but in the meantime. And then on the other hand, the unguided modes decay with the distance. Okay, so if you have a bunch of atoms in free space, then what you will have is that, the interactions between them decay with the distance, such that if they are very far away, eventually what you have is recover what you recover is two atoms that are emitting independently from one another. Okay, but this you cannot do if you have two atoms in a nanofiber. No matter how far you put them, they always talk to each other. Okay, because the interactions kind of go through the nanofiber, and there's translationally invariant. Let me explain you a little bit then what that means in terms of these decay rates that I was telling you about before. Okay, I told you about the superradiance and subradiance. So now I have an array of atoms, and now I have this A, which is the nearest neighbor distance. Okay, so I'm going to, what I have taken here in particular is 15 atoms in a chain, and I have diagonalized this matrix here, this gamma JL. Now, the first thing that I'm showing you here is in free space, okay? Let's consider there is no nanofiber. Okay, no nanofiber, I can do the diagonalization of that matrix, and that gives me all the possibilities of decaying, so to say, that the system has. Now, if the atoms are very far from each other, and note that if I say far, I have to say compared to what, obviously, in any case. So A divided by lambda is what sets, so to say, lambda being the distance between the ground and the excited state. This is what sets, so to say, what's far and what's close. So if the atoms are far, as you can see that all of the decay rates basically collapse into the single atom decay rate. Okay, so I recover in free space, as I said before, all of the atoms are independently emitting with their own decay rate, single atom decay rates. Now, when they are very close together, on the other hand, I get something different, right? I get that all of a sudden I have these, for example, these states that are superradiant, and then I have a bunch of them that are supradiant, okay? So I have this collective, but this is not really what I'm looking for, so I just wanted to show you also for comparison. Comparison to what? Now, what happens if I only consider the guided modes? I do not consider now the unguided modes, only the guided ones. Let's assume that my atoms are only coupled to those all-to-all modes. Then what I get is that basically independently of the distance between the atoms, I only have two possibilities, okay, two modes that decay with some decay rate. Okay, I have this mode, and actually this mode corresponds to a photon being emitted into this direction, okay, to the right. And then I have another mode where, this represents the probability, the possibility of atoms, photons being emitted into the other direction. So this is literally just, this is the decay rate into the guided mode that goes to the left, and this one is the decay rate of the photon that goes to the right. Okay, this is only the fiber. The truth is somewhere in between, because now I have to consider everything, because that's what I'm doing. And if I now consider both free space and the fiber, then I get something that is a hybrid between the two, okay? So I have, particularly what is interesting here is that I have so I have basically the same as in free space, except I have this funny looking state up here with a decay rate that is much larger than the rest, okay? And that one, looks very much like as if it was this guided mode, okay? And of course, I wouldn't be talking about it if it wasn't. We checked and it is, okay? So basically, the eigenmode of dissipation corresponding to this decay rate that is large corresponds to a photon process in which the photon is emitted from the chain into the right propagating mode only, okay? So not one and a bit on the other direction. No, it's, I have a photon shared among all of my atoms, and now this propagation mode tells me a process in which that photon is emitted into the nanofiber and then goes to the right, all of it, okay? So think about this for, what this means later for directionality, because if I can actually now take that mode and excite exactly that mode, then I'm in business, okay? But I will talk about it in a second, because that means that the photon that I emit is going to go into that direction necessarily, okay? But, okay, basically here I'm repeating what I just said, okay? I have a hybrid, so to say, super-radiant mode, that it's also very kind of clearly visible, so to say. So it's the decay rate is also much higher, which means also that more photons are emitted, so to say, or the emission rate is higher into this mode. And then let's look at it. Let's analyze this particular state at some distance between the atoms. Okay, so I put A over lambda equal to 0.8. And now what I'm going to do is I'm going to have a look at, this eigenmode. So this is just the rate, okay? But I can always write that mode as some sort of, okay, let's call this phi s, and then this is just, okay, proportional, no. This is equal to some sum over all atoms, okay? So let's say J equal 1 to n, I have n atoms. And then I can write this as the modulus here, Js, let's call it, times e to the power of I phi s. No, sorry, phi s, but phi n, phi j. Okay? So what I have is, I'm going to literally just take that mode and look at it. Okay, and I'm going to look at what's the amplitude across. So if I look at it physically in space, how does it look? And I'm going to also look at how its phase changes across space. And what I get is the following. So I get here, and here I know that there are many lines, but I'm going to ask you to look only at the black ones, okay? For some reason, okay? So if you look now at the black line, what you see is that basically that state corresponds to a state that is equal superposition, equal weight superposition of all atoms being excited, okay? So all of the atoms are excited basically with the same weight. And then, more interestingly, if I look at this phase, that phase, you can see that has this gradient across the lattice, okay? I mean, you only have several ones because I plotted it between minus pi and pi. So you can see that the gradient is always the same. The good thing also is that gradient depends on the distance between the atoms, and you can extract the exact distance, so to say the gradient between two atoms, and you can write it as A times Kf, where Kf is just a propagation constant. It's very similar to 2 pi over lambda, okay? Just very similar, so to say, to the propagation constant of the laser, minus 2 pi times n, okay? And n is just an integer, a natural number with a 0, okay? So you can really just obtain analytically an expression for that gradient. Now, why do I want to do that at all? Well, the reason is that now what I'm going to do is, why don't I excite that superradiant state, and then I collectively enhance both the beta factor, so the amount of photons that are emitted into the guided modes, and also the chirality. And obviously this is how we do it. We take a laser field that has a given angle. Remember this angle, okay? And I set that angle such that it excites something that has exactly this phase profile. Okay, so this is what I'm doing here. And the good thing about this is also you can actually extract exactly what the angle between the atoms, the momentum of the laser and the array has to be. And you can get this superradiant phase matching condition or geometric Bragg condition, because it's basically, you can obtain this from, in a way, from geometric analysis, basically. And you can obtain a formula that tells me exactly what this angle has to be in order for this superradiant state to be matched, okay? So this is what we did, and well, here I'm going to show you some results about this, but which results am I showing you now? Okay, what I'm going to analyze is I have that system, I have a particular angle, okay, of the laser, I have a particular distance between the atoms, and then I just analyze the emission rate into the right eigenmode. So I have a detector, and then I can calculate this analytically from the master equation, okay? So note that I'm taking just the master equation and I'm basically solving this expectation value. And then I'm just taking this and I'm convoluting this with the part of the emission that takes care of the emission into the right. So this is, remember that I had this gamma JL and I broke it down into 3 pieces, one for the unguided, one for the right, and one for the left. So basically this is telling me if I emit a photon, what's the probability that I have emitted it into the right mode. And that's what I'm going to do. So basically, this is what I get. So let me also analyze it a bit more. So here what I have is the angle, so I have this theta, and then I also have this A over lambda, okay? So the distance between the atoms. And then you can see that this I'm measuring the collective beta factor. What's the collective beta factor? So it's the probability that if I have one photon in the full chain, what's the probability of that photon being emitted into the guided modes with respect to the total emission rate. And you can see here that there are these lines. So in general, you get something that is very similar to what you get in having one atom, which is about 15%, I think here, well, which is just the blue, so to say, area. But there are some lines that give you a huge enhancement. For example, here, this is for 15 atoms only, okay? I have 15 atoms, and then I get, something like 75% beta factor. Okay, so this is a huge enhancement of this beta factor. Moreover, what you can show is that indeed those enhancements, okay, those lines, you obtain actually by using this geometric Bragg condition. Okay, so these lines that I plotted there are literally just what I get if I plot this this condition on top of this 2D plot. Now, another good thing is that this beta factor goes up with the number of atoms, and here you can see that it kind of goes up. Okay, so for this was for 15, I think this was for 17 or so, and then you were already on the 80%. Okay, so it eventually saturates to 1. Okay, so you can really get, for large enough number of atoms, that all of your photons are not lost. okay, but actually going into the nanofiber. You can also increase the chirality because what I just said, right? I mean, you are exciting one single mode. That mode actually is the one that propagates to the right, which means that if I look at the what I call collective chirality or the directionality, okay, it's exactly the same quantity that I was showing before. This is very close to one along those lines. You can see that this is basically, yeah, just exactly one. And actually, this is very, even for very small system sizes, you already get this huge chirality enhancement because basically, yeah, you are just, yeah, hitting exactly the state that goes into the right. So out of this, what I have is that many atoms with the right angle, yeah, driven by a laser that is at the right angle, gives me a huge enhancement of the beta factor and a huge enhancement of the directionality of the coupling. So I get that every time I have a photon emitted, I emit it into the right and only to the right. Okay, so basically that's what I get out of this. So this is a cool message, I find. But now we also saw, analyzing a bit, yeah, what happens if you now, okay, what happens to the light, that if you now look at the spectrum of the light, so if you change now the detuning, okay, and then you start looking at how many, yeah, actually having hit the spot, so to say, and not, changes the spectrum completely. So here I show you two possibilities of the spectrum. Here, so this is delta, okay, so this is the detuning of the laser. And as you can see here, for example, this gives you just, yeah, a typical Lorentzian, very nice and easy. On the other hand, if I look at the light that comes out at very close to this geometric Bragg condition, all of a sudden I get something that has the maximum of resonance, actually, okay? I have a double peak, so to say, structure. And this is what we wanted to understand a bit better. And this is what we did next, and I'm going to show you in the next 3 slides. I'm going a bit over time, but we also started quite late, so I hope I'm okay. Danny?
No problem at all.
Danny, tell me something.
Hello? I'm saying that
Sorry?
there is no problem. Yeah, we definitely started later than.
Good. So then, okay. So then I show you this. Okay, what we wanted to know what happens now to the spectrum in particular, and then we said, okay, let's look at this same quantity that we were looking before. So this gamma R. Now I am normalizing this by the scattering rate of one single atom into the into the fiber, okay, so that you can see the difference if there is enhancement or not or whatsoever, okay, but this is just, yeah, the same quantity. And now I plot it for values varying theta and also varying the detuning, so that I have basically, yeah, the spectrum at different values of the angle. And as you can see here, this is quite cool because when the atom of excitation, so the angle of excitation is very far from this geometric Bragg angle that I was telling you before, what you get is what I told you. Well, I have some sort of Lorentzian shape. Of course, it has kind of structure, but okay, the farther you go away from this angle, the more it looks like a boring, so to say, Lorentzian. That's what happens usually. But now, as you can see here, the more I get closer and closer to this geometric Bragg angle, the more, yeah, something happens. In particular, at exactly the Bragg angle, what I get is what I told you before. I get a splitting now of the peak into 2 different peaks. I have not only a splitting into 2, which is very clear, okay, but I also get a huge enhancement of the scattering rate of this emission rate into the right angle bond, okay? So you can see here that this is 120 and this is kind of 25, okay? I get this huge, yeah, enhancement. But if you think that's huge, then we looked and we realized, okay, but okay, if that is big, what's that, right? Because this is even bigger. And actually, if you make a cut again in this spectrum, for example, there, you can see, okay, this is 500 times, okay? You can even have higher enhancement. And this is not at the geometric Bragg angle. And, well, we wanted to understand exactly what was happening here, okay? And because typically, I wouldn't expect anything to be better than the geometric Bragg angle. And in order to understand this, the full master equation was a bit too complicated to deal with this. So we took help from a simplified model. That's what we do in theory, right? When we cannot understand something too complicated, we go to a simpler model. And here, what we have is, okay, we consider in this simplified model, I have the same master equation, basically. It's just that I throw away some parts, okay? What I throw away, for example, is any interactions that are unguided, okay? I consider still that you can emit into the unguided modes, but I consider that all the interactions, because they decay with the distance, all of those interactions that decay with the distance that are mediated by the photons in the radiation field that is not in the waveguide or in the nanofiber, those are gone. And I'm also going to consider that the emission only happens into one direction. I'm going to consider from the beginning full chirality, even for one atom, okay? Again, this is a simplified model, and I will show you that this simplified model later fits the full model also well, okay? But this simplified model is good because it allows me to calculate things analytically. And in particular, if you go through a couple of pages of math, what you realize is that the emission rating to the right can be calculated very nicely, and you obtain this kind of formula out of it. Now, in this formula, what I have is here, this K effective, which is just K0. This is just the propagation constant of the laser. So this is 2 pi divided by lambda, okay? So just keep it in mind, times the cosine of phi, which is the emission angle, the driving angle, plus this Kf, which is, I showed you before, this Kf was just the propagation constant in the nanofiber. It's just slightly different from the propagation constant in vacuum, so you have to consider that. So that's this K effective. Another thing that appears is this T, and in a minute it will make sense why. Okay, it's just a function of of the beta factor for a single atom, the total emission rate, and the tuning of the laser. And finally, what I also have kind of pushed outside of this sum is all of that, is this the scattering rate, and this is just the scattering rate of a single atom. If I have a single atom and I look at how many photons are emitted into the nanofiber, this is the value that it takes. Okay, so this is just, it has just a Lorentzian shape in general. This actually, it's nice because you can understand it. You get it analytically. This is really from the master equation. You kind of make these simplifications, and then at the end you get that. But you can also understand this in a more physical, so to say, way by looking at literally just emitters that are emitting one by one, and then you just look at difference of paths in the light that that they have with respect to each other. So, for example, I have a laser field, and now I have this. The laser field kind of hits this atom, the green one, so to say, and then that emits a photon. And now, what happens to the next atom? Well, the next atom I hit it a bit later, so to say. So I have this extra phase lag. And on top of that, I have another phase lag because it has to go through the nanofiber. So I have this other phase lag. So this added with that gives me this part over here, this e to the power of im k effective A. But then there is another effect, which is now the light goes near the first atom. And that means that you have some sort of absorption and dispersion. So that absorption and dispersion are actually given by this T, okay? And that T then is just the complex, it's just a complex valued parameter that is just telling you the absorption and the dispersion due to the presence of another atom. And then you can do the same with another atom farther away, and then you have this kind of, this phase lag. Then you have, this has to walk twice, so to say, that amount of time. So you have extra phase lag because of going in the nanofiber. And then eventually this one hits 2 atoms instead of 1, and then you have this T squared and this 2 times the argument of T. So that's basically the also you can obtain basically from spec. So that gives me some analytic function, and okay, once we have analytic functions, what you want to do is analytical predictions, which is nice for a change. So in particular, what I want to do is I want to look at the scaling of the scattering rate with number of atoms. And the good thing is that, okay, this formula here, I can basically, this is just a sum, and this t is always anyway smaller or equal to 1, so I can literally just, make the sum, okay, because, I mean, formally speaking, because it's just an algebraic, so it's just a sum, and it converges, and this is what I get, okay, and so far this doesn't tell me a lot, but n, okay, keep in mind, n is just the number of atoms, but if you look at it carefully, this tells me actually a lot. For example, I have this b, which I have defined, is just the argument of t minus k effective times a. Okay, what I can see is that here, the emission rate for a fixed value of theta and for a fixed value of the detuning is going to oscillate actually with the number of atoms. So the scattering rate displays these damped oscillations with the number of atoms. The damping is given by this absorption, okay, the absolute value of t to the power of n. And then basically you can see that indeed, okay, what I have is these oscillations, and they get damped, and eventually they saturate to a given value, okay? And that value will obviously depend now on the other parameters of the system, okay? But as I increase the number of atoms, I increase it, then what I obtain is just oscillation, and then eventually a saturation value. Okay, I cannot go just up with the number of atoms, I get a saturation value. And again, just touching base, look, I mean, the exact numerics, really not the simplified model, but everything in, gives me things that are very similar. Okay, you see you can reproduce these oscillations, and I mean, the value is very, very similar to the simplified model. Now, let's look again, okay, at that formula, and then try to understand what happens to at the geometric Bragg angle, okay? Because there, we know what happens, right? We know it because, okay, we knew it already before. What you see is this double peak structure, and then what we can actually now analytically obtain is how the distance between these two peaks, that I'm going to call delta max, scales with the number of atoms. And also I'm going to calculate how this maximum value scales with the number of atoms. And again, I can do this analytically now. And what I obtain is the solid line. So this is how the maximum, this peak, this separation between these two peaks goes bigger and bigger and bigger with the system size. And in particular, you can see here that it's increases linearly with the system size. Again, these values are the numerical values. These are just the values of the simplified model. But on the other hand, what you can see is that this maximum scattering rate, okay, the value of this maximum actually saturates for large system sizes, okay? So it doesn't just grow eternally, so to say, it just saturates to a given value. Still, you get a huge enhancement with respect to other angles, but it still saturates. So the question is, okay, we know that we can do better, right? We know that there are these two peaks that, okay, we would like to know how to get. But the good thing about this is that if you look at this expression, you can know that the actual maximum of this is going to be achieved when this b is a multiple of 2 pi. Because there you don't have oscillations. Everything depends only on the absolute value of this t parameter, okay? And then you can, again, obtain analytically out of that a formula for the cosine of the theta MB, which is the modified Bragg angle. That's why we call this modified MB, modified Bragg. Okay, and you can see that the difference with respect to this one is just this argument of t divided by k0a. Now, this corresponds indeed, I mean, if you plot now that on top of the numerical data, so this, remember, this comes from the simplified model, and you can actually plot this on top of it, and you can see that, okay, this hits really the spots where the emission rate is maximum, and this is the cool part here. You can also look at how this, okay, you can see that the scalings within are completely different in this particular point with respect to what you get for any other point in space, okay? So in particular, and this is kind of the interesting thing, the maximum scattering rate, so this black peak, so to say, grows proportionally to n. It doesn't saturate, no, it actually goes proportionally to the with the system size. So here, for example, in the simplified model, you can see it very clearly, but also this, again, these blue dots are obtained from the exact evolution of the master equation. And you can see that, so that means that, the more you increase the number of atoms, the more you increase the scattering rate, contrary to what you get with other angles. And that, in turn, gives you scattering rates that are huge, even with respect to what you obtain for atoms in free space. So you can even make the system grab more of the light that comes from the laser and emit it into the guided mode. It's really, noticeable.
Sorry, one question. Do you have any intuition about because I understand that you have calculated this angle just by maximizing the rates.
Exactly.
But the geometric Bragg angle, I understand that there is some intuition behind it. Do you have any intuition of why this angle?
No, okay. As I say, I mean, the intuition that one can see is that it comes from the fact that for the geometric Bragg angle, what one doesn't consider that the light actually passes other atoms, so to say, interacts with other atoms as it crosses, so to say, the system. And here you can see that the modified Bragg angle actually considers the fact that there is a dispersion because of the light kind of being absorbed and a bit dispersed. So you don't consider the photons being just emitted, emitted and never seeing the medium again, but actually you consider that the photons are being emitted, still seeing the medium, and then leaving the medium. Yeah.
And for other angles, do you know if the scaling is linear, or does it saturate for all angles but this one?
For all of the angles, what you get is that the maximum scattering rate just saturates.
Okay, so this is the only one that does not.
Exactly. This is the only one at which you actually get something that is not a saturation, but actually growing proportional to n. Yeah.
I see.
Yeah.
Cool.
Then just a very quick last thing. I told you that, also the simplified model considered that all of the photons were emitted into one direction from the beginning. And the problem is, of course, that for getting an analytic result, we cannot really, it gets more and more complicated if you consider that photons can also be emitted into the other direction. But we still have the numerical results. And what you can see here is that, look at this emission rate, for example, and we calculated for completely symmetric emission. So this is d equals 0 for a little bit bias going into the right, and the one that I have shown you already completely going into the right. And as you can see, for both angles, basically all of these scalings, they remain the same, qualitatively the same. So you still get a linear scaling with n for the modified Bragg angle, and still you get some sort of saturation that goes into a saturating value for the rest of the angles. So the scalings remain unchanged no matter what you do with the directionality. And this is important if you want to, for example, have a real system and you want to see these effects, because as I said before, you cannot really control the directionality of a single atom. You only can do it up to a point. So usually what you have is things that indicate directions. With experimentally, so they were particularly interested in knowing what happens if you have actual problems that people have in experiments. For example, in practice, what you can put atoms next to a nanofiber, which I find already quite impressive, and you can put them in a lattice, but typically your lattice is not going to be perfectly filled. Actually, far from it. What you're going to have usually is that you have basically half of the sites being occupied and half not. And then this is what we did here. We compared basically what is, how good basically the results are for imperfect filling. And we even did fillings, okay, here and here what we have is a filling of 50%. So 50% of the times you have so we took a lattice, we filled it with 50% of the atoms randomly, and then we made many evaluations. And I'm not going to go much into the details, but what you can see is that qualitatively, all of the results are exactly the same. So you still get the same results, even if your atoms are half of the time, so to say, there. Okay, so all of them are still there. And this brings me to the conclusions, believe it or not. So what I have shown you is, okay, the emission from a chain of atoms into the modes of the nanofiber can be collectively enhanced and also made perfectly unidirectional, exploiting the fact that you have collective states, so to say, and collective interactions. Also that these all-to-all interactions actually, you can see them in the light, because all of a sudden you have shifted resonance, you have, your spectrum doesn't look the same if you are actually emitting a lot of photons into the guided modes, that if you're only emitted once upon a time, one here and one there. And finally, I have shown you that you can actually make the scattering into those guided modes even more enhanced if you have angles that deviate a little bit from the geometric Bragg angle. And with this, I thank you very much for your attention.